Hey, good morning, guys. All right, so any questions? So before we start, guys, are you guys all understanding all the concepts or you're finding difficult to understand and to follow? Are we going on a right pace or do you think I'm going too fast?
The thing is, I think we have to go through the recording.
Okay.
Yeah, I mean,
So
that
so
is
as I
required.
mentioned, yeah, as I mentioned again, what's your name? How you pronounce your name?
Yeah, it's Agye. Agye Uda.
Again. Okay. So again, you show, as I mentioned multiple times, that you have to set your schedule in such a way that whatever I'm teaching, you have to revise on the same day. Okay, so go through the recording, create your notes, and go through the handouts. If you do that only, then only you can able to match the pace. Otherwise, things will get pending, and later you will find difficult, to cover up all those topics. So yeah, it would be little uh, tough, during the course to take out time and to revise all these things. But that discipline you need to follow. Otherwise, I'm only saying it is going to be difficult later. And because see, if I'm teaching any topic today and if you revise it, that would be fresh in your mind, right? And in that case, if you miss out something, if you then you can easily get it if you go through the recording or if you go through the handouts through that material. Uh, but if you miss out and if you do it later, then everything would be new for you, and it may take time for you to understand all those topics later. So do that, and exercises also. I'm giving us short, use cases, small use cases with a very toy data set examples so that you can understand the concepts. Here, the most important part is to understand the concepts and how we are applying it to solve the problem. So that's something you need to understand uh, clearly. And if you are not getting it, why we are using it, how we are applying this, then there is a problem. I hope at least application part you is clear for you guys, right? So why we are using this classification and how we are using it, what kind of value we are getting out of this model. So that's something has to be very clear. So let me know anywhere if you are finding any challenges, let me know. Okay, I'll try to help you out. It's not something you're coming in this class, listening, and then that's all. Okay, and after that, you're forgetting whatever we have discussed. So that is not going to work. As I mentioned, these are like this is a science, and there are so many concepts. Remembering everything going to be difficult. Okay, so until unless you practice, until unless you read multiple times, go through that particular topic multiple times, it would be hard to remember all those things. And after a while, if you don't do that, everything will be mixed up in your brain and you will get confused. Okay, whether it is a KNN or whether it is a K means, which is again another different algorithms. So you will get confused. So my humble request is take out at least 2 hours in a day from your personal. Cut your sleeping time or cut any other, uh, take out time from any other activities, but give 2 hours in a day. That would really help you out. All right, so we will start. Thank you.
Your voice is not coming.
I'm so sorry. I was talking on mute. Yeah, so today we will talk about logistic regression, which is one of the statistical algorithms for classification. So yesterday we talked about KNN, which is more of a mathematical based algorithm where that particular algorithm can be used for numerical prediction as well as for classification. So in statistics, there is another algorithm known as logistic regression, which is used for classification. So when I'm saying classification, again, it has certain um, shortcomings that this logistic regression cannot be used for multi-class classification. It is used only for binary classification. So what do we mean by binary classification? If in your output variable, if you have only two categories, then only you can use logistic regression. And that classification is known as binary classification. And you will be surprised to know that most of the classification problem, I'll say close to 70% of the classification problem, business problems are binary only. See, in our daily lives also, mostly decision would be whether we should do it or whether we should not do it. Can I go for it or can I shouldn't or should I don't go for it? So mostly the decisions would be binary, right? Shall I invest in this or shall I not? Shall I go to the office or shall I don't? Okay, so most of our, if you see 60 to 70% of our decisions are based on go or no go, yes or no, right? Whether we will pass or whether we'll fail, right? So even in the business, most of the use cases for the business are mostly binary classification. So for example, if I have to do the defect classification, whether it is a defected or whether it is not defected, right? Whether the customer will buy my product or it will not buy my product. Okay, whether the my sales will happen or not happen, right? So whether machines will fail or not fail. So typically, business would like to know that whether they should move forward or not. Okay, so for those kind of cases, binary classification um, is the solution. And moreover, even when we are making this decision, now our business would like to understand why the model is predicting as yes or why the model is predicting as no, right? So they would like to understand how the predictions are happening. So in the linear regression, we have seen, right, the variable which are significant, we can able to understand, right? We can able to interpret from the model. So those models, linear regression models are explainable, right? So when the businesses are making decisions, then they should also understand, why they are making that decision. So that statistically or that from the data, they should able to uh, get that kind of information. When compared to the KNN you have seen yesterday, right? There the variable importance is missing, right? It will just tell, okay, which of the data points are similar. But while making the predictions, which variable is of higher significance, which variable is of high importance, that something is missing in that particular model. Though the KNN may give you a better accuracy or better results, but understanding and interpretation of that particular model would be low when compared to these statistical models. Okay, so now let's understand this logistic regression, how it works. And it is kind of derived from the linear regression, and some level of transformations we have to do so that it will fit to a classification problem. Linear regression is more for a numerical prediction. We'll take that concept, but we will do certain transformations so that it will fit for a classification problem. So that's the reason this logistic regression are called as generalized linear model. Generalized means we are kind of making some transformations on the linear model to fit to a classification problem. In short, we call as GLM models. Okay. So here the logistic regression is a classification algorithm for categorical variables, and that too a category which has only two categories, okay, in it. Now again, we have independent variables, we have dependent variables, right? Yesterday we have seen a similar data set, but there we have multiple categories, right? Customer categories 1, 2, 3, and 4. Here we have only one. Here we have only two categories, and the name of the dependent variable is churn. I hope all of you understand what is churn. The people who don't know, let me explain. The churn means the customer who has left the company, um, and even you hear this churn for employees also. Okay, employees. So when we say attrition, means employee leaving the company, and sometimes we also call employee churn. So churn means people leaving. Okay, it could be customer or it could be employee. So for example, this particular customer was with that particular company for quite some time, and in one particular day, that particular customer left that company and he moved to some other competitor. Okay, he started buying products or services from other company. So that is considered as churn. Okay, yes. And now this is very, very important use case for every business. Okay, if you can predict the churn beforehand, that this particular customer is going to churn in next few months or in next 1 year, okay, then you can retain those customers. And then again, this is a marketing strategy how you want to retain. People may give offers, people may give discounts or give some extra privileges. In that way, they can retain the customers. Even for the employees, if the model says that this particular employee is going to churn, okay, then probably better hikes or better position may be offered to that particular employee if he is worth and if the company is willing to retain that particular employee, right? So churn is very, very important, because to predict the churn is very important, because acquiring the customer is much more costlier and it takes more efforts when compared to customer retention. If you have an existing customer, then to retain that particular customer would be relatively easy when compared to acquiring a new customer, because you are getting a regular business. So in the telecom, it's a telecom data. Every month, he's paying the bill, right? So you are getting a regular income. And if he's a premium customer, then you are getting a good amount of revenue from that particular customer. So let's suppose he churn, okay, he left your company and go to some other telecom service provider. So that recurring revenue will decrease. So now to acquire a new customer and that customer being a to get into that kind of premium category, it will take a lot of time. And to acquire one customer, there is certain statistics like you have to almost 4 times or 5 times number of customers you need to target. Then only you can acquire one good potential customer. So that much efforts the business has to make, to acquire a new customer. So that's the reason now businesses focus more on in monitoring these customers and predicting which of the customers may churn, okay, in the near future, and then taking the strategic decisions, to retain those customers. So this is the use case which we will uh, do it on Python, okay, and we will see that how this problem can be solved by using logistic regression. Again, in the logistic regression, we can have input variables as continuous as well as categorical variables. And in this data, you see that there are certain categorical variables like equipment, call card, wireless. Okay, these are all categorical, and there are the continuous variables. Okay, so there are various applications. As I mentioned, 60 to 70% of the business use cases are binary classifications only. Okay, so for example, in the healthcare, whether the what is the probability of a person having a heart attack Okay, what is so these are all insurance use cases. What is the mortality of the injured patient? So uh, this is the first time, we were working in the insurance use case, and this was kind of, we got surprised that insurance companies, they predict whether the person will die or not. That is known as mortality, right? So, and based on that, they plan uh, the policy premiums and all those things. What would be the lifespan of any particular person? That's something insurance companies they predict. It's surprising, right? Somebody is predicting when a person will die, right? So, so such kind of crazy things, now businesses are doing, because see, now insurance companies, if they just like that, if they go and start giving the insurance, sell the insurance policies, definitely they may incur a loss. Okay? And you see that when you are buying an insurance policy, they ask a lot of details, right? Your they regarding your health, they ask you to go through medical tests, they ask for your schedule, your job occupation, everything they will check. And then they will feed all that data into a model which will predict what is the lifespan, okay, of a particular person. Okay, if it is like somebody met with an accident, then based on his condition, they will predict whether what is the chance that this person will die, right? So based on that, these will do. I don't know how ethical it is, but people are doing this, okay, and we were part of that particular use case. Now, predicting the customer's propensity to purchase a product, okay, or whether they will subscribe any particular service, okay. So for that also, there is you can use this logistic regression. So basically, logistic regression gives you a probability. We discussed about probability of success, probability of failure, right? So it is between 0 and 1, right? If the probability is closer to 1, so that means there is a high chance of a particular event to occur. If it is close to 0, then there is a low chance of that particular event to occur. So it is completely binary. If the probabilities are like zero point 0.1, zero point 0.2, that means there is a less chance or less likelihood that particular event would occur. So now you see all these are the events. Getting an heart attack is an event. If the probability is close to 1, that means there is a high chance. Okay, predicting the mortality of the injured patient, if it is close to 1, the probability, then it is a high chance. Customer propensity to purchase, predicting the probability of failure of a given process or a product. As I was talking about machine failure or process failure, for that also you can use logistic regression. Okay, and the likelihood of anybody, defaulting a particular uh, loan payment. So there also banks or insurance companies, they are using this logistic regression. Now, in this logistic regression, once you are predicting, you will understand why any person may default on a particular payment. Okay, what factors may influence any customer, to default. If the business understand those parameters, those factors, now business can focus on that particular part. Okay, and if anybody is kind of um, showing some kind of signs related to that particular parameter. For example, if that person's income is going down, okay, so there is a high chance that that person may default any particular loan. So now these are the important parameters which the business will keenly monitor, because they know out of 100 variables which are the important variable, which are the important parameter which they need to monitor, which they should monitor uh, to control these defaults. And in the for the banks and for insurance companies, this default is a big problem. You might have heard about NPA, non-performing assets. This is and now this is such a big problem for banks that this, if it becomes bigger, then even the banks get bankrupted. You might have heard about US recession some few years back. what happened? People have taken mortgage loans. Okay, mortgage loans, they because they were not getting jobs. So what they did is they just put their houses on mortgage and they took loan. But because as they were not having jobs, they couldn't able to pay the loans back. So because of which the banks got has got a higher NPA, which is non-performing assets. Okay, so because their income, the bank's major income is through these interests. Okay, loan interests. So now if people are not paying, as they have given entire money to the public, so now they do not have any net assets with them, and even they are not able to get it back from the customers. In that way, most of the banks got defaulted, bankrupted. Now, that's the reason it has become very important for the banks. First of all, the major use case for banking is whom to give loan or whom not to give the loan, right? That is first decision they have to make. After that, once they have given the loan, now they have to monitor which people may default or may not default. If the people are may if there is a high chance of any person to default, then they will monitor and then they will uh, uh, keep chasing that particular person, to make the payment. So now, in fact, you might have seen there are certain applications which say that in 5 minutes we will approve your loan. How it is being done? Let's suppose if there are 100 applications for a loan, it's very difficult for the banks to process those loans manually. So there, these companies they are using these machine learning algorithms to predict, okay, what is the to who all people they should give the loan, and for who all people they should reject the loan. So there are multiple use cases, uh, which can fit to this binary classification problem. So if your data is binary, as I mentioned, the output variable, if it is marked as 0 or 1, yes or no, true or false, or any two categories, if it is there, okay, then you can go with logistic regression. And if you need a probabilistic result, if I say that there is a 99% chance that this particular stock is going to will go up in the next 1 week. Okay, so definitely you may invest because I'm telling you with 99% confidence or with 99% probability, right? So while making the decision, if you want some kind of probabilistic output, okay, based on which you can confidently you can go and make the decisions. So for that, for those kind of scenarios, logistic regression is a suitable algorithm which you should use. Okay, this something this you can ignore. Okay, here we are not going to make any linear decision. Okay, but here we are not making any kind of a linear regression model, but what we are trying to do overall is if you have two classes, we're trying to come up with some kind of a boundary, okay, for these two classes. Okay, so now again, this particular boundary is a line of an equation, right? Beta 0 plus theta 0 plus theta 1 x1 plus theta 2 x2 and all those things. Just you have to think about like if I have two categories, how can I differentiate those two categories? How I can have some kind of a boundary between those two categories so that I can decide which decision to make. Okay, so that's something we make some kind of an assumption. If that happens, then that would be good. So in those kind of scenario, we can go with logistic regression. And if you need, this is very, very important, if you need to understand the impact of a feature, as I mentioned, business would be more interested like, okay, if the model is predicting as yes, why it is predicting as yes? To which particular variable it is giving more importance? And then they can validate, okay, yes, definitely this is the most important variable, right? And we should focus on this particular variable. So, and now this slide is very important, guys, because this tells you where to apply logistic regression. So application is more important. You may directly jump to KNN because KNN is easy and it will give you better results. But if your business is looking out for this, okay, and the last point where they need to understand the impact of a feature, which is more impacting, which is not significant, there you cannot answer through KNN. So your focus should not be always to build a accurate model. Okay. Sometimes even a lesser accurate model, but with better explainability would be the need of the hour. Okay, so in that case, you have to choose these statistical models rather than choosing those machine learning algorithms. All right, so here, what we are going to predict now. Okay, so this is my actual. Now, what we want from the model. From the model, we need probability. Okay, so we want a model which can give me the probability values. I don't want direct categories to be displayed as the output. Rather than that, I want a probability. For example, it may give like 0.83 for this, 0.92 for this, 0.10 for this. So these are all probabilities. The probability of a person or of a customer getting churn. So this particular customer, let's suppose my model is predicting, saying that there is a 83% probability that this particular customer would churn. So now you can keep a threshold. For example, if you say any probability which is more than 0.5, then I will mark it as 1. So that means that person, there is a high chance or high likelihood that person may churn. Wherever it is less than 0.5, I'll mark it as 0. So like that, you can label, okay, based on the probability values. And depends, okay, 50% probability, I've taken it as that's a general notion, right? People, if the chance is more than 50%, then people will prefer it that that particular event would occur, right? But for some of the scenarios like life sciences and healthcare, where they don't want to take risks, their threshold would be higher than 0.5. So um, if the model is giving the probability greater than zero point 0.6 or zero point 0.7, then only they will consider that that event would occur. Otherwise, they will mark it as 0. Okay. So it depends on the use case to use case to case, like what could be the ideal threshold for for that particular scenario. So here it is a conditional probability here, what this particular logistic regression model is going to predict. So it is saying probability of y equal to 1 given x. And what is this x? These are all input variables are considered as x. When given that tenure is 11, age is 33, address is 7, income is this, so and so forth. If all this values is provided for these input variables, what is the probability that this person would churn? So that is this conditional probability which this model is going to predict. And you know all, right, what is conditional probability, right? Now, what would be the probability of y equal to 0 of not getting churn? It is 1 minus this. Because only two things can happen, right? Either the person will churn or he will not churn. So there is no other possibility. So these are mutually exclusive and collectively exhaustive, right? So if the model is predicting the probability of a churn, then if you want to calculate the probability of not being churn, then you just subtract that probability by from 1, then you will get the probability of y equal to 0 given x. Now let's understand what is the difference, major difference between logistic regression and why we need to transform something, to fit that into a classification problem. Why there is a need of logistic regression in the first place. Okay. So for example, now let's suppose we fit a linear regression on this. Okay. You can try also. You can consider this as a numerical column, and you can try multiple linear regression. It will give you some linear equation, okay, which is something like this, right? So here, basically, it will give the line which would fit um, on these data points well. But when it is, so here I'm predicting the customer income. I'm trying to predict the customer income. For predicting the customer income, it works well because here the points would be scattered, right? As the age is high, the income is also high. So here you will see that these points would be all over the line, right? But when it comes to classification, here in this particular case, churn, I have only two categories. My all points will lie here only, okay? And here only. It will not go here, it will not go down. Okay, this is the on the y-axis, this is the static place for these two categories. Because there are only two values, 1 and 0. There is no other value. Okay. So it is limited to only these two categories. So I will get only this. Now, if I go and fit a linear line on top of it, does it make sense? First of all, it will not make sense. If my x1 is increasing, how based on this particular equation, I can decide whether it is from category 1 or category 0. Okay. So it will not solving the purpose. And on what basis shall I make the decision? Because here with this linear equation, I can get any value, any numerical value. How to understand that numerical value? How I can tie up with these categories? One way is like, for example, here, I can put some threshold saying that, okay, if whatever this linear regression is predicting, for example, let's suppose zero point 0.5 or something. Okay, I can say that if the values are greater than zero point 0.5, then I will mark it as 1. I'll put them into this particular category. If the output is less than zero point 0.5, then I will mark it as 0. But do you think that is the right approach? Okay, if it wouldn't be a right approach because see, now I just took it as zero point 0.5, but in all the cases, it would not be that simple, right? You have how you will decide on the threshold because it is completely continuous. And this with linear regression, you can get any value between minus infinity to plus infinity. So what should be the middle value which you should consider above which? And now this is a very possibly, with the linear regression, this kind of a problem can be solved where you are seeing a very distinct positions of, category 1 and category 0. In some of the cases, you will find that, okay, you will see a red category here also, okay, and blue category here also. In that case, this linear regression will not work at all. Okay. So what to do? Now, this is the problem, okay, with the linear regression. Okay. So here in this linear regression, this is the problem that, okay, it can go to any range, the output, because your output equation is in this form. Now this is a linear equation, as you keep on increasing the x1 and x2, the y will also increase. So there is no limit. But what we want probabilities. Okay, we are looking out for probabilities, and we know that probability has certain limits. Okay, it could only range between 0 and 1. Now I want that kind of an output. Now what I will do is I will make some transformation to this linear model. So the sigma, if you're seeing, right? Okay, now this is my linear equation, theta transpose x. Okay, so this is nothing but this equation. Okay, theta 0. So don't get confused with beta, theta, right? So in some of the books it is beta, some of the books it is theta. So these are all coefficients and these are all my input variables. So the matrix multiplication between these two matrices will give you this equation. So this is my linear model, which is denoted like this. Now, to fit to a classification problem, there is some need of transformation. So now the sigma sign, you can consider it as some kind of transformation. We have to transform this linear model in such a way that whatever output is coming, that output should fall within this limit between 0 and 1. Okay, so here this is the y-axis. If you see, the value is between 0, okay, minimum, and the maximum is 1. So we call this curve as sigmoid curve. So instead of a straight line, I'll rather prefer a sigmoid curve. Now this is a non-linear, uh, and this curve is non-linear, right? So now this, if it is non-linear, definitely the equation of this particular curve would not be a linear equation. So now we will understand what is the equation of the sigmoid curve. And this in short, people also called as S curve. Okay, it is in the form of S, it is S-shaped. So alphabet S-shaped. So there's a reason it is called as S curve. Now let's understand, what kind of transformations are applied on this linear equation to fit to the sigmoid curve. So now one transformation, so this is known as logistic function, or in short we call as logit function. So now this is the logit function. Okay. Now instead of having a linear equation here in the y-axis where we were getting a linear line, now I am going with this particular function, which is the transformation of this linear model. And what is the transformation? This is the transformation. Okay, now this is the formula for a sigmoid curve. Now you just you can play with this equation. Just take something like 1.2 plus 2 times of x. Okay. Now you give any value of x here. Okay. Anything from minus infinity to plus infinity. You put any value into this x, you will see the output will be between 0 and 1. So that's the beauty of this equation, this mathematical equation. Now this is the equation of the sigmoid curve. So this is the function fx, okay, which is 1 minus 1 plus e raised to power minus theta t x. Now, this kind of a transformation happens. So first it will find out this linear equation and then it will transform that into this particular equation so that all the values will be between 0 and 1. Okay. Now we can say that, so as the output of this equation is between 0 and 1. Now we can say that the probability of y equal to 1 given x, which is our main objective, right? We want to predict the probability of the event to occur, right? Given that this is the scenario. You can mention it as 1 plus e raised to power e minus theta t x. So these x is nothing but your input variable. Now again, how this equation, how this basically now, how this algorithm will get trained, how it will come up with the final model. That's something, okay, we will understand now. So for that, again, some transformations will happen. Give me a second. Yeah, sorry. Yeah, so there is another, so we need to now predict the probability of y equal to 1 given x, which is given by this particular equation. Now, the results coming out of this equation would be between 0 and 1 now. Okay, now, but how this algorithm would get trained and how it will come up with these optimal values of theta. In the linear regression, we have seen that there is a cost function, right, associated to it, which is MSE, mean squared error, right? But does that mean squared error can apply here? We cannot, because here it is a category. Here we cannot calculate the error. Okay, here we have to go with something else. Okay, so here this MSE would not work because this MSE would only work if you are dealing with a numerical prediction. For classification, we have to go with some different cost function. Let's understand, what is that particular cost function. Firstly, there are some important transformations which will again happen, to convert this particular non-linear relationship again back to a linear relationship. So here, in some of the books, it is like 1 minus, I'll just put it as capital X. The capital X, you can consider this particular equation. So in some of the books, it is mentioned like this. In some of the books, it would be mentioned like EX plus 1 minus EX. Okay. So these are the same equation. So if you want me to prove it, let me prove it. So I just multiply e raised to power x on in the numerator and in the denominator. So if I multiply with this, so now you will get this because this will get cancelled and you will get this particular equation. So in some of the books, it would be 1 plus e raised to power minus x, where x is nothing but your this linear equation, or somewhere, it will be written like this. Okay. Okay, so now let's suppose my probability of success y equal to 1 given all the input variables x is equal to e raised to power x plus 1 plus e raised to power x. Now tell me what would be the probability of y equal to 0 given x? So it would be 1 minus e raised to power x plus 1 plus e raised to power x. Okay. So it would be 1 by 1 plus e raised to power x, right? So this would be the probability of failure. Now with these two equations of probability of success and probability of failure, we will go and calculate the odds ratio. Okay, we call as odds ratio. Odds ratio is nothing but the probability of success. And guys, it's all mathematics. Okay, if you're finding it difficult, you can ignore it for now. So odds ratio is the probability of success divided by probability of failure. Now, if you go and use this equation here, what you will get e raised to power x. And I mentioned this x is nothing but your equation, right? Linear equation. Now, still it is not a linear equation. It is the exponential of the linear equation, this odds ratio. So to convert back to a linear equation, what we will do is we'll take the log of the odds ratio. And if you remember the mathematics, if you take the log of exponential, so exponential will go away. Okay, so you will be left with x, which is nothing but theta t x. Now, earlier what we did, we converted the linear equation into a non-linear equation by using that sigmoid curve function. Now, after that, what we are doing now, again, that sigmoid curve function, which is non-linear, again, we converted that into a linear form by using this log of odds ratio. Now, what it will do is now mathematically or compute from a computation perspective, now this would be easier for this algorithm, to compute and to come up with the optimal theta values. Okay, but the cost function will be different. So it would be similar kind of a convex function. Cost function would be here, and these would be x. Okay, sorry, the betas. Okay, now it will find out the beta, which will give you the minimum cost function. But here the cost function is not an MSE, it would be a likelihood. Okay, now what is likelihood? We will understand too much of different topics. So just think about it. Okay, in the linear regression where we were predicting the numerical values, we have to come up with a model which gives me a result which is very much closer to the actual value, right? If the actual value is, let's suppose, 100, I will look out for a model which will give me the prediction closer to 100. So there we will calculate the error. Now here in the classification, our objective is to predict the probability, right? Now here I would like to measure, here it's not an error, okay, which will work here. Instead of that, I will use a likelihood function. What is likelihood function? For all the ones, if I go to this data set, for all the ones, I want a higher probability. If my model is giving higher probability, for example, for one, let's suppose it is giving me 9.5. There is one model, model one. And for this, it is giving 9.8. Higher confidence, the model is predicting with a higher confidence that this person will churn. And actually, that person has churned because I have the actual data. Now, this is turning out to be a good model, right? And for the people who haven't churned, I want the model to give a very low probability. So for example, 0.001, okay, or 0.02 or point something like this. Okay, it's a very small value, right? If I have the model like this where the probabilities are on at an extreme, the probabilities are extreme. Okay, so these are extreme values, very closer to one and closer to zero. If the probabilities are closer to one for uh, for the positive cases, then my model is good. If the probabilities are close to zero for my other category, then my model is zero. Let's suppose I have another model like this, M2. Here, let's suppose it is giving the probability like this. 3 and probability 4, 5. Now, this model is also good. It is also doing a pretty good job, right? If I take a threshold as 0.5, with this model also, I am able to predict correctly. But look at the confidence level. So now, if I ask you which model is good, what you will say? This one or this one? M1 or M2?
M1.
Of course, M1, right? Because now M1 model is giving me the better probability values. With this model 1, I have a higher confidence to make decision, right? Because one model is saying there is a 95% chance that this person will churn. So I'll go with this model rather than going with the model which is saying there is a 70% chance that this person will churn, right? So now here, instead of error, I will go with a likelihood. Now, what is likelihood? Likelihood means, overall, how confidently my model is predicting the outcome, that is called as likelihood. So how you will calculate the likelihood? So for the first case, X1 or the Y1, I'll say P1. Okay. So the probability of success, okay, for the P1, for the observation 1 into 1 minus P. I'm just putting as 1 minus P. Okay, this is for first observation. I will multiply with other observations too. So overall probability I will find out. Okay. So here, let's suppose P1 is 0.95. So what would be the 1 minus P1? It would be 0.05. So this is for first observation, the probability of success and the probability of failure, both. Okay. Now here I will, for the P2, 0.98 into 0.02. So like that, I will find out the dot product for all the probabilities, for all the observations. Now that would be my likelihood. Now, to in short, we can put it like this. So these are all dot product. So these are multiplication. So in mathematics, multiplication sign is this pi and summation sign is this sigma, right? So here I'm saying this is the multiplication of p yi equal to 1 given xi into pi 1 minus p So for all the observations, I will take the probability of success and probability of failure together and I will multiply. Now that is known as your likelihood. Okay, so now what is this? This is likelihood of all observation of class 1. Okay, y equal to 1. Now what is this? This is the likelihood of all the observations of class 0. So now if this is high for class 0 and this is high for class 1, okay. So for example, in this case, what is the probability of failure here? This particular value is probability of success. So what is the probability of failure? It would be 0.999 something, okay, 0.99. So it is high, so this value would be higher. So overall, the likelihood would be high. Okay, so now I can compare between the two models, M1 and M2. I'll take these values and I will put that into this particular equation. I'll see for which particular model the likelihood is higher, and then I will choose that particular model. Now, how this algorithm works is like it will change the beta coefficients and see that for which particular set of beta coefficients the likelihood is higher. Okay, but things are not that easy, to compute this kind of equation. Okay, so there some level of transformation again people have done on this likelihood to convert that into a kind of equation which can be computed easily. And in mathematics, basically instead of a equation with dot products, okay, the product equation is much more complicated to process rather than they will go with a equation with a summation. So now what kind of transformation will happen is instead of likelihood, we will prefer log likelihood. Now you might have, if you remember the mathematics of logarithm. So what is the log of x into y, guys? If anybody remember?
Log x plus log y.
Log x plus log y. Perfect. So here, this likelihood, which is the product of this, I will go with log likelihood. So what will happen? So it will become, instead of this product sign, now it will come as summation. Summation of log of this particular term. Okay, and in short, I'm just writing as p y equal to 1 plus summation of log of p equal 1 minus p equal p y equal to 1. Okay. Now this would be easier for the algorithm to optimize. Always remember, if you want to optimize something, then the equation has to be in a summation format. Okay, in the summation form. Now this is known as log likelihood. Now there is another problem now. Okay, we have heard about gradient descent, right? So what gradient descent does is it minimizes, it works on the minimization problem. It doesn't work on the maximization problem. Here I have to choose a model which will give me a maximum likelihood, right? Or maximum log likelihood. But this particular problem I cannot fit into a gradient descent. I cannot give it to the gradient descent algorithm because the gradient descent algorithm only work for a minimization problem. We have seen, right? It always descent. It will always try to find out the minimum point. It cannot find the maximum point. So what easy way of doing it is just put minus sign to it. Okay, let's put minus here. Now this will become a minimization problem. Now this minus log likelihood becomes my cost function. Now this gradient descent will try to minimize this minus log likelihood, this particular term overall, or different set of these beta parameters or the coefficients, and it will find out the best parameter which is giving me the least minus of log likelihood. Now too much of confusion, right? So if somebody asks you what is the cost function, just you say log likelihood. And this particular algorithm will try to maximize the log likelihood. Just you tell that. Internally, when you are running the algorithm, this kind of transformation is happening automatically. Okay. So it will add minus and it will convert this maximization problem into a minimization problem, and it will give it to the gradient descent to come up with the optimal values. Now I'll take a pause. Let me know if you have any questions or did you understand this? So what we have done, again, I will give a recap. Okay, where is that? We talked about this, why we can't use linear regression, because the linear regression will give you any value between minus infinity to plus infinity, and based on that, it would be difficult for you to come up to identify the threshold and to categorize observations. It is something, okay, which is not trivial thing. Okay, you cannot do it. So that's the shortcome of this linear regression. So for that, we are going with a logistic regression. In the logistic regression, we will do some transformation to this particular linear equation. And that's the reason this model is called as generalized linear models. And what we are doing is we are converting this linear equation into a sigmoid curve, right? And the property of this sigmoid curve is that whatever input value you feed to this particular equation, the output will be between 0 and 1. And that's something what we need, because we want the probability values, and the probability values also range between 0 and 1. So that's the reason we have picked this particular curve, and which would fit well for this logistic regression problem. And now that function is called as logistic function. So we have seen how this logistic function look like. And now again, to convert this non-linear form to a linear form, again different set of transformation needs to be done. So where the probability of y equal to 1 is given by this formula, we can derive what would be the probability of y equal to 0 by subtracting this particular equation from 1. So now we got this particular equation. Now after that, we calculated this odds ratio. Odds ratio is nothing but the probability of success by probability of failure. And then we have substituted this equation. Now we got this particular equation, which is exponential of your linear equation. Till your equation is not a linear, it is an exponential equation. Now to convert the exponential equation to a normal linear equation, we take the log here, so which is called as log of odds ratio, and that would be your linear equation. So this is how, I can again transform the linear equation, non-linear equation into a linear equation. Now, once the linear equation is done, here we cannot use MSE because it's all about classification. Where is that? Yeah, here is all about classification. So here the error would not work. Okay. So for that reason, we are going with a likelihood function, and we have seen what is this likelihood. It is the dot product of probability of success and the probability of failures. And again, from a computation perspective, likelihood, this kind of equation, we cannot give it to any particular program, to optimize, because the product equation generally, to process it would be hard. So what we did is we converted that into a summation, right? Equation. So by taking the log on the either side. So now this likelihood is called as log likelihood. Somewhere you will see in the book, people call it as cost function as maximum likelihood, or they may call as maximum log likelihood. Okay. So now you understand, why they are somewhere likelihood, somewhere log likelihood. Okay. And for internal computation purpose, now this will be converted as minus log likelihood, and now it becomes a minimization problem. Okay. Is this clear, everyone? I know you may have to revise, so please revise. I'll show you here. Now see, this is the cost function. Okay. So they have taken, somewhere you will see that they will take the average also, okay, for this, just for faster computation. So it is minus. So minus is there. And now this is your log likelihood. Okay, so this hat is nothing but this you can consider as P of y equal to 1. Okay, this one. Now what is happening here? This yi and 1 minus yi. What it does is one single equation. What it will do is, with one single equation, uh, you can segregate the probability values of successes and the probabilities of failure. So let me give you an example. For example, you have one row which is marked as 1, another one marked as 0, then 1, then 0, let's suppose. Now, based on this particular model, I have calculated the probabilities of success. Okay. So let's suppose it is 0.6, 0.3, 0.8, and 0.1, let's suppose. Okay, so we have seen that likelihood is nothing but the probability of all the successes uh, for the observations which have been marked as 1 into the probabilities of all the failures the observations which are marked as 0. Now, who will segregate this, right? These probabilities of 1 and 0. So for that, they have come up with one standard equation. So here, if you go and substitute, for example, this y, these are the actual values like 1, 0, these are the actual values. This you multiply with this particular log of this probability. So let's take the first observation. It is 1 into what is the probability of success? It is 0.6. Now, for the same observation, what is 1 minus yi? It would be 1 minus 1 because actual is 1 here. Okay, so now this term will become 0 into log of, sorry. Guys, you may have to again hear this back, okay, this recording to get more understanding, better understanding, sorry. Okay, so this is log of 0.6. It is 1 minus 1 log of 1 minus 0.6. This is the first observation. Now, what will happen is it will automatically segregate. Now, this is for success, right? So now it will take this particular equation and this will automatically will become 0 because 1 minus 1, this term will become 0. So that's the reason this entire term will become 0. Now, let's take this 0, 1. Okay, this 0 observation. This you plug it into this equation. Now, what would be your first term? The yi is 0 into log of 0.3. Okay, plus 1 minus 0 into log of 1 minus 0.3, right? Now, in this case, now this will become 0. Okay, this will become 0. And now it will consider this particular term only, right? Automatically, if you're seeing that it is segregating uh, the observations, based on these categories. So for all the ones, it is taking this particular probability of success. And for all the zeros, it is taking the probability of failure, which is 1 minus the probability of success. So this is that equation, right? So now this becomes your cost function. Now this cost function, we will use, and give it to the gradient descent to minimize and to find out the optimal best parameters. So to find out the best parameters of the model, it will minimize the cost function. And how it will minimize, it will use the gradient descent. And what is the gradient descent? A technique which uses the derivative of a cost function to change the parameter values in order to minimize the cost. It's all partial derivatives and all those things, okay, come into picture. So I'll not get into that particular level of mathematics because nobody asks all that particular things, right? Now, see, this is n-dimensional view of this particular gradient descent, where it will randomly start from some location and gradually it will go down, 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 and it will look out for this global minimum. And every time it will do the partial derivatives. If you have n number of input variables, so that many number of times it will take the it will go with the partial derivatives. Okay. So that's how, it will iterate and finally reaches to the minimum point. If somebody is interested on this particular mathematics, I'll share you one paper. You can go through it where they have explained the entire mathematics around gradient descent. If you are interested, I'll share that. Okay. So now the complete recap. So first, it initializes the parameters randomly. Okay, this gradient descent. It calculates the cost function. So here the cost function would be the likelihood. Okay, which you can consider it as an error. Then it will it will calculate the gradient slope of at that particular cost function and see that whether it will move forward, it can go down or not. If the gradient is downwards, then it will go further down and it will update the weights with new values, and then again it will repeat. Okay, from here. So this repetition will iteration will be done again and again and again and again till it reaches to a point where the gradient is equal to 0. Okay, so that means the slope is 0. So gradient is nothing but the slope. So wherever the slope is 0, the model will converge and it will stop. And those would be the optimal parameters. So that's about the logistic regression. And this logistic regression model will also give you a similar kind of summary as we got in linear regression. So with that, we can understand which of the input features are important based on the p-value, and we can understand which of the parameters are of higher significance. So I'll stop it here. Let me know anybody has any question. So you guys digest all these things. Meanwhile, I'll open up the use case. Major questions in the interview, what people may ask around logistic regression is, they may ask, first is the cost function. Okay, so what is the cost function this logistic regression considers? Okay, that you have to answer. Second question would be on the evaluation part. Okay, so once you train the model, how you will evaluate model. Okay, so that also something, okay, we will discuss. Okay, so if there's no questions, then let me jump into multiple evaluation metrics. Okay, in the classification, you will find a lot of evaluation metrics. Yeah, so please, I request you to go through it multiple times because there are too many concepts here in this particular topic. Okay, so first one would be your and we will see in the use case also. Okay, there would be one in the model summary. There is a term known as deviance. So deviance is nothing but -2 times of log likelihood. Okay, so this is one of the measure, okay, which explains how much is the, you can consider it as as an error. Okay, so -2 times of log likelihood is called as deviance. And in the linear regression, we talked about R square, right? So here also there would be an R square, And what is the definition of R square? R square is a measure which captures the amount of variance captured by the model. But here we cannot use the same formula because there we used errors and residuals and all those things, right? So here we cannot use that because for the classification problem, in the classification problem, we cannot go with an error. Okay, we cannot, because error is primarily we calculate when we are dealing with a numerical variable. So here we will call this R square as a pseudo R square. It is not the exact R square which we have discussed in linear regression. It is more of a pseudo R square. So in the R square, if you remember, okay, we were comparing the model with the null model, right? What was that null model? Null model was the mean, in that case, linear regression. Here in the classification problem, here the null model would be mode. For example, in your data, mostly people have not churned. Okay, so there are only few people, 1% or 2% of the customers they have churned. So if any, for any new customer, if you want to predict whether that person will churn or not, typically you will go with maximum. Okay, you will say that he will not churn. Okay, that is nothing but the mode, right? So that is, so for example, for every prediction you are saying it, they will not churn, they will not churn, they will not churn. How much accuracy you are getting? Okay, you are just blindly, you are uh, going with mode, right? In your data, there are maximum people who haven't churned, and you are considering that other people will also not churn, right? So that is my null model in this case. So what I will do is I will find out the model deviance. You know how to calculate the log likelihood. The same deviance we will calculate for the null model also. So 1 minus your model deviance by null model deviance will give you a pseudo R square. Now this will also range between 0 and 1. If your pseudo R square is close to 1, so that means your model is a good model, okay, and it is kind of giving you a better results, and it is better than your null model, okay. Now this is something, okay, you will automatically get when you print that model summary, okay. So you remember in the stats model.api, we were printing that whole model summary, and we were getting a lot of different statistics about the model, right? So there you will find these deviance and pseudo R square and all those things. This is for your understanding how that particular these metrics are getting calculated. That's something, okay. To understand, I've given you this particular explanation there. Now there is once the model is trained, now you're testing on the test data set. There you will use certain. This is for model. If you want to understand the model, how good your model is. Now these are the metrics. Now after testing, when you test or when you evaluate, you will look out for certain metrics. Okay. For that, you have to build a confusion matrix. And you are again going to get confused because the matrix name itself is confusion matrix. So what it is, so it is a 2x2 matrix. So actuals and the predicted. In the actuals, I have only two classes, right? I have 0 and 1, right? And when I'm predicting 0 and 1. Okay, based on whatever probability threshold I will consider. Ultimately, I'm categorizing the observations into these two categories. Now, if I'm predicting as 0 and actually that observation is also 0, then these are known as true negatives. Okay. If I'm predicting as 0, but actually that particular observation is marked as 1, then these are known as false negative. Okay. And if I'm predicting as 1, but actually it is 0, then what it is called? It is called as false positives. And this is called as true positives. You might have heard about this false positives and all, right? We have heard it a lot during that COVID time, right? People were talking about false positive cases, right? Uh, People are getting detected as COVID, but they were not having COVID. Okay, so those are now known as false positives. Even there are certain false negatives also, because the people with some asymptomatic symptoms, right? So they were having COVID, they were carrying that COVID, but those were not getting detected. So those were known as false negative. Okay. So as they are saying that they are not having COVID, but actually they were having COVID. Okay. So those were like false negative cases. So these are our problems. Okay. False positives and false negatives. Definitely any model cannot be 100% accurate. Definitely there could be some amount of misclassification that model may do, right? Where it is one, it may mark it as zero. For example, loan application, right? If if let's suppose there is a one eligible applicant, but my model has predicted as zero, okay, saying that okay, this application should be rejected. It would happen, and that's the reason the manual intervention, the manual supervision is required. We cannot give completely to these systems. We cannot run the business with AI, artificial intelligence. There has to be humans because they may do certain errors. They may do certain commit some misclassifications, right? So to test whether my model is a good model or not, I'll run that model on my test data set. Okay, and then I'll come up with this confusion matrix. So how I can come up with this confusion matrix? In my data, I have actuals, I have predictions. Okay, based on the probability values, I can mark those okay as one or zero, right? Now I have to compare these two. Now actual is one, my prediction is one. So these are known as true positives. Actual is zero, my prediction is also zero. These are true negatives. Actual is one, but my prediction is zero. So that is false negative. This is true positive. This is false positive. This is false negative, right? So like that, I can count how many are true positives, how many are true negatives, how many are false negatives, false positives, and then I can come up with this confusion matrix. Okay. Now, once you have this confusion matrix, now based on this, there are multiple matrix, okay, which you can calculate. Let's first talk about the most important matrix known as accuracy. Can anybody tell me how can I calculate the accuracy based on these four values? It is simple. Just think logically, you will get it. So accuracy is what? Accuracy is nothing but your correct predictions divided by total number of predictions, right? Out of total predictions, how many predictions are correct? That is nothing but your accuracy. So in this particular term, it is nothing but what is your correct predictions to true positives and true negatives, right? So these are all your correct predictions. What are your total predictions? It is summation of all true positives, true negatives plus false positives plus false negative. So this is an equation for accuracy. Okay. So all the true predictions divided by total number of predictions is nothing but your accuracy. If you want to show an error, then it is 1 minus accuracy. So now you can, so it is defined as FP plus Fn divided by Tp plus Tn plus Fp plus Fn. This is your formula for error. You need not to by heart. Just remember this confusion matrix. Okay, with this matrix, you can easily derive these particular equations. Okay, now comes your precision. The formula of the precision is true positives divided by true positives plus false positives. So predictions means precision means how precisely your model is predicting positives. Okay. In any of the use case, there would be one category which is of more importance for the business, right? For you, let's suppose whether to invest or not to invest. Investing is the most important decision, right? If I mark it as not to invest, not to invest, not to, nothing will happen. Okay, so you will not invest. But if the major decision is to which kind of investment options my model is predicting as one, okay, and advising me to invest, that is of more importance for me. Even for machine failure. Okay, if the machine is not failing, that is okay. Fine. But if the machine is failing, if it is marking as if the probability is high that this machine is failure, that is of my interest. Just a second, guys. Hello? Okay, so precision means how precisely my model is predicting positives. Because any business would interested like, how accurately my particular model is predicting the positive events. Okay, because the positive events are of their interest. Okay, because these are rare events. Okay, so machine would not fail every time, right? It will fail once in a while, right? So there would be only few positive observations, labeled observations, which shows the machine failure incidents, right? So my interest is like how this model, how good the model is predicting those positives. So that is of my interest, right? So for that, I will go with precision. So what precision will do is it will understand out of all the positives, okay, which this model is predicting, what is the ratio of true positives. So let's suppose it has predicted 80 positives, okay, and out of 80 positives, only 40 positives are true positives. So 40 by 80 is my precision. Okay. Now, this is on the model side. Okay, precision. Now, there is another measure known as recall. Now, in some of the cases, people would be interested to know out of total actual positives, how many times my model has predicted true positives. Okay. So here in for the precision, as we were looking, sorry, as we were looking into this particular row, so this is for precision. So this is my total positives, predicted positives, which model is predicting. And out of this total positive, I am calculating what is the ratio of these two positives. Recall is this. Out of total actual positives, what is the ratio of true positives? So recall is true positives by true positives plus false negative. Okay. So it has multiple other names also, which I will not confuse you right now. Okay, I will not mention. So in some of the use cases, people will concern about precision. In some of the cases, people will concern about recall. If now I ask you, which do you think is more important? Probably you may not able to answer because both precision and recall seems to be more important. Seems to be important, right? Both the metrics sounds important because this is also important, right? Out of the total positives, how good your model is predicting the positive, that is also important. And how good your model is predicting positives out of total actual positives, that is also important. So for that case, if that's the scenario where both these matrices are important, then I will go with one particular matrix known as F score, okay, or we call as F measure. which is equal to 2 times of precision into recall divided by precision plus recall. So if both the things are important, then I will just look at F score, because F score comprises of these two matrices, okay, together. And all these precision, recall, F score, everything, these all will range between 0 and 1, guys. Okay. So there is no problem in such, like, to evaluate based on these metrics to consider which model is better. You can easily do it, because if the values are closer to 1, so that means your model is giving a better score. Okay. So I will stop it here. Okay. So these are the important metrics: accuracy, error, precision, recall, F1 score. Okay. There are few more. Okay. So which I will cover in some other, when we will discuss about some other algorithm, but these are the most important ones. Okay. When it comes to classification, binary classification. So we will now, as we do not have time, so I will suggest you to go through the recording today, and tomorrow we will discuss on that particular churn prediction use case. Okay. So do not mug up this equation, guys. If you mug this equation, definitely you're going to get confused. Okay. With these true positive, true negatives, false positive, you will not remember. You will get confused. There's a reason this is called as confusion matrix. Okay. Better, if you want to recall, if you want to remember these equation, just in your imagination, in your memory, just frame this particular matrix. This should come into your brain, this particular matrix. And with this particular matrix, you can derive these formula. When it comes to recall, you have to consider this particular column. When it is precision, you have to consider this particular row. Okay. So if you remember these two, then automatically you can able to derive the equation correctly. But do not mug up. Why I'm saying not to mug up? Because in the interview, people may ask the equation. It happened. Okay. So for that reason, I'm saying do not mug up. Because generally people will get confused between precision and recall. Because there is only this particular term which is getting changing. Okay. So even if you feel that it's very easy to remember, but not. Okay. Sometimes you may get confused whether it is a false positive or a false negative. That's something may lead to a confusion. All right, so that's all for today. If you have any questions, feel free to ask. Okay, so if no questions, then we will wrap up. So let's connect tomorrow. Thank you.